So first of all, let's determine if this sequence is an arithmetic sequence. And if so, we're going to write a formula for the nth term. So we've got 114, 106, 98, and 90. What do you think? Is it arithmetic? Yes. Why is it arithmetic? Because the difference between these two is -8, right? Common difference is -8. Okay? So if we wanted to write the nth term for this, the explicit sequence, what would we do? The way I like to think of arithmetic sequences is like it's linear. Does that make sense? Our common difference is our slope. So -8 is our slope. If I take -8 times n, we almost have it, but I have to have my b, which would be my term 0. So what would be my term 0 here? What is it? 122. Because if I take 122 and subtract 8, I get my first term. I take 8 away again, I get the second term. Take 8 away again, I get the third term. Okay. What would be the recursive formula for this particular one? A sub 1 equals 114, and a sub n plus 1 equals the previous term, right? A sub n minus 8. Okay? Everybody good with those two? Okay? Now let's look at the next example. Is 1, 4, 9, 16, 25 arithmetic, geometric, or neither? If it's geometric, it has a common ratio. If it's arithmetic, it has a common difference. So is there a common ratio? Is there a common difference? There's not, is there? First common differences are not the same number, right? But what happens if we find the difference between the differences? Difference between the differences is 2 consistently, right? So if the first common differences are the same, it's arithmetic. It's like linear. If the second differences are the same, what do you think it's like? Quadratic, second power. Everybody kind of agree with that? Because aren't these powers? 1, 4, 9, 16, 25, are those squares? Okay, so what could our sequence be here? When n is 1, we get 1. When n is 2, we get 4. When n is 3, we get 9. What is it? N to the second power. 1 squared, 2 squared, 3 squared, 4 squared, right? Okay. So this is neither arithmetic or geometric. It's actually quadratic. And we can recognize if it's quadratic if we see that our second differences are the same. Okay? So far so good, haven't lost anybody. Okay, let's look at the next one. Don't have to draw the figure. Exactly. If they're all 2s or all 1s or all 5s or what have you. Here the first differences was 3, 5, 7, 9, not the same number. So we don't have a common difference on the first time around. But if I subtract them again, I end up with 2, 2, 2, 2, 2. So that meant it was quadratic, yep. If the first common differences have been the same, it would be a linear or arithmetic. But the second common differences makes it quadratic. Okay. All right. So we've got a figure, a geometric figure, not a geometric sequence, but a geometric figure made from geometric figures, right? Squares. So we started out with our first iteration, our first number, having 4 edges, the yellow box. And the second one has a total of how many edges? Well, the original 4 plus 4, 4, 4, 4, so a total of 20 edges. Okay? Then we added another row on. I put teal around them to show you which ones are new. Okay? How many edges are we going to have here? 32. So 32 and 20, which was what we had before, is a total of 52 edges on our third box, our third image. Okay? Then I put a row of red around the outside. So how many are we adding to our 52 now? How many edges will we have? We'll have 100 because we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times 4 is 48, and 48 plus 52 is 100. Okay? Our fifth iteration, thank you, is going to have a total of how many? 160, because we added, everybody agree with 160? Okay. And then we could extrapolate the sixth one, but we're not concerned about that at the moment. Okay. Now, let's look at our first differences to see if this is arithmetic. Okay. Difference between 4 and 20? 16. Difference between 20 and 52? 32. Difference between 52 and 100? 48. Difference between 160 and 100? Definitely not arithmetic. 164? That makes sense. We forgot one. Is it taking 16? It's like adding, so the next row we would add 1 here, 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 and here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, plus 6 more would be 20. Right, so, yeah, so now second row, what's going on? 16, 16, 16. Definitely quadratic, right? Everybody cool with that being quadratic? Okay. So we can actually come up with an arithmetic or a quadratic sequence, a formula that fits that. And we do that by realizing that a quadratic always has the form ax squared plus some bx plus c, right? That's the standard form of a quadratic equation. Okay? In this case, though, we like to use n's because we've been dealing with sequences and series for a while. So is everyone okay with me saying a n squared plus b n plus c? Good with that so far, right? Okay. So now what we're going to do is we're going to say that when n was 1, we got back 4. So a sub 1 is going to be sum a times 1 squared plus sum b times 1 plus sum c, and it's equal to 4. One equation with 3 unknowns. Okay. A sub 2. When n is 2, that means I have an a times 2 squared plus b times 2 plus c, and it's equal to 20. So 4a plus 2b plus c equals 20. Two equations, still 3 unknowns. So what do I have to do? I want to solve for a, b, and c. Do I need a third equation? Okay, third equation, let's use 3. 3 and 52. So a sub 3 equals a times 3 squared plus b times 3 plus c, and that should be equal to 52. So 9a plus 3b plus c is 52. Okay, now I've got 3 equations with 3 unknowns. How do we solve a system of equations with three variables, 3 unknowns? We use subtraction, elimination. We can use matrices. We have all kinds of tools in our belt, right? Okay, most of you are probably going to want to use systems of equations. If we're comfortable with that, then an augmented matrix. Okay, so let's eliminate c, because I see c in each one. Plain old 1c, 1c, 1c. Everybody good with that? So let's take the bottom one minus the second one to get rid of a c. So equation 3, a sub 3 minus a sub 2. Okay, so 9a minus 4a, 3b minus 2b, c minus c is gone, and 52 minus 20. We've eliminated one variable. I took the 9a minus the 4a. I took the third equation minus the second equation. 3b minus 2b, c minus c, 52 minus 20. Okay? Let's do that again. Let's take second equation minus first equation, because we'll get rid of our c again. Okay? So we're going to take a sub 2 minus a sub 1. So 4a minus a. 2b minus b. And 20 minus 4. Okay? So we've eliminated c's. Ready to get rid of the b's? Okay? Yep, subtract. So if I subtract, I'm changing the signs of all. 5a minus 3a. b minus b. 32 minus 16. So what's a? A is 8. Now plug it back into one of these two equations to find out what b is. 3 times 8 plus b equals 16. 24 plus b is 16. So taking away 24 from both sides. b is equal to -8. Now finding a convenient place. I like this one, it has less to do. So this equation right here, we know a is 8, b is -8, plus c equals 4, so c is 4. Okay, so we have found a sequence for this, a formula for it, where a was 8, b was -8, and c was 4. Good review of system of equations. It's a lot of work, and you're only going to have like 5 problems. Okay? Because our second differences were consistent, therefore we know it has to be quadratic. Yep. So that is like it's like a arithmetic sequence that we had before, only now we're dealing with quadratic. On these, this one right here. Gotcha. Okay, so initially we had just one. The first iteration was 1, 2, 3, 4 edges. And then the second one had those 4 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 20 total. Okay. Most of the time you won't have a pattern, a picture like this. I just wanted you to see how this can relate to real world. Yep. Yep. Okay. All right, here's another example. Okay. So we're going to find the model for the sequence. So first of all, figure out what the differences are. Is this guy going to be arithmetic, geometric, potentially quadratic? So what are the first differences? 5, 7, 9, 11, 13, right? Okay, definitely not arithmetic. So I'm hearing quadratic. Why is it quadratic? Yep. Second differences are 2, so we know it's quadratic. Okay. So now that I know it's quadratic, I know that my sequence will be of the form a sub n equals sum a n squared plus sum bn plus c. Sign your planner real quick. Okay. So when n is 1, a sub n is 5, right? Put it in the wrong spot. Hoping it's Tuesday already. Okay. So a sub 1 is going to be, substitute 1 in for every n, a plus b plus c. And what's a sub 1's value? 5. Okay. A sub 2. A sub 2, I'm going to plug 2 in everywhere I see n. So I'll have a 4a plus 2b plus c. And what is a sub 2 equal to? 10. Third equation. 9a plus 3b plus c, 17. You're going to get really good at solving systems of equations with this particular pattern. Okay? And again, you can use matrices. You can use Gauss-Jordan elimination. Lots of ways we can solve these. But it's a good review for our final to use our systems of equations review as well. Okay? So I started to get in a pattern with these. I said, okay, let's take bottom minus second. It doesn't have to be. But you're going, if we do that, we'll get a 5a plus b. C minus c is gone. 17 minus 10 is 7. If I want my b's to go away, I can actually take the top minus the second equation. Easier, because I'll get a negative b for the next time. So a minus 4a, b minus 2b, c minus c is gone, and 5 minus 10. So this came from a3 minus a2. And this came from a1 minus a2. Now we add them up. 5a minus 3a and 7 minus 5. So a is plug it back into either equation, probably the top because we like to deal with positives. 5 times 1 plus b equals 7. What's b? And then I like to plug them into the top equation, the first equation, because I only have to deal with, you know, with the no coefficients here. So 1 plus 2 plus c is 5. So c is 2. So our sequence for this one, our formula for this sequence is n squared plus 2n plus 2 is our a sub n. You guys good with these? I have another example I can show you, but if you're good with these, then I can turn you over to the assignment and you'll have plenty of time to work. Okay? Let me show you the assignment. If anybody wants to see another one, we can do that. 5 problems. Section 9.4, 55 to 60. Page 643.